Hi, I'm a presenter Yesong-yoon in the team of Professor Ha. Our topic is the effect of various seed layer on agglomeration. The contents of this presentation are as follows. Let me tell you about agglomeration first. Agglomeration is a phenomenon where thin films condense at high temperatures as shown above picture. The surface energy and thermal stress of the thin film are important factors in the process of agglomeration. Surface of the external layer has unstable energy and thermal stress. It means that Gibbs free energy is a positive number. So, the surface tries to minimize the exposed area to be stable. The thin film shape changes depending on different conditions. Specifically, we traded samples to make dot form like this picture H, and it called nanodot. An ultra-thin transition metal is deposited between the substrate and the metal layer, which is called the seed layer. Titanium, cobalt, chrome layer were deposited between the magnesium oxide substrates and silver layer. Depending on the material used in the seed layer, agglomeration phenomenon can be promoted. We call this seed layer assisted agglomeration. In SLAA process, the insertion of an ultra-thin transition metal used as seed layer changes thermodynamics and stress state between the silver upper layer and the substrate. Next, we'll talk about the advantages of SLAA method. First, we can make a thin film with strong adhesion to the substrate. In other words, it can improve the durability of the thin film. Second, it can reduce the temperature of agglomeration, so we can save energy. Third, the epitaxial growth of the nanodots strengthen the thin films. It can be applied to electronic or magnetic device manufacture process. Fourth, characteristic nanostructures reflecting substrate surface symmetry are formed. It can be applied to optical devices or sensors. The picture of the bottom right is a schematic of what we've done. We annealed the samples for 5 hours at 350 degrees Celsius, 400 degrees Celsius, and 450 degrees Celsius to form a dot structure. Thin samples were fabricated in order of the above figure. Next, I will explain the deposition process. Thin deposition process was performed by DC magnetron sputtering. A seed layer of various epitaxy layers of each thickness was deposited on the magnesium oxide substrate. Silver upper layer was deposited sequentially on a coated substrate with a thickness of 4 nanometer to 7 nanometer. After deposition, the samples were annealed maintaining between 350 and 450 degrees Celsius for 5 hours. And samples were analyzed by X-ray diffraction, atomic force microscope, and scanning electron microscope equipments. It is a condition of deposition process. Each deposition rate using DC magnetron sputtering was shown above. Moreover, we maintained pre-sputtering process for a long time to stabilize plasma and to control impurities of target. Next, we will discuss experimental result and discussion. Each figure ABC are AFM images in the size of samples A 1 micrometer, B 5 micrometer, and C 10 micrometer when titanium was used as a seed layer. And each figure DEF are AFM images in the size of D 1 micrometer, E 5 micrometer, and F 10 micrometer when cobalt was used as a seed layer. This result indicated that cobalt seed layer did not assist agglomeration, but titanium seed layer did. Each graph indicated change of A coverage area, B nanodot mean size depend on thickness of silver upper layer. This results show that seed layer assisted agglomeration phenomenon has critical point of upper layer. This is the XRD data of MgO TiAg bilayer sample according to silver thickness A 4 nanometer, B 5 nanometer, C 6 nanometer, D 7 nanometer. This result indicated that nanodot grows epitaxially following atomic arrays of magnesium oxide substrate in direction of 111. This is the XRD data of MgO CrAg bilayer sample according to Ag thickness A 1 nanometer, B 2 nanometer, C 3 nanometer, D 4 nanometer. This result indicated that nanodot grows non-epitaxially following atomic arrays of magnesium oxide substrates in direction of 001. Let me summarize the conclusions of this study. Nanostructure thin film based on the self-assembly process were studied by changing material and thickness of bilayer on a single crystal magnesium oxide substrate. Through AFM results from various samples, it is confirmed that the material and the thickness of the seed layer act as an important role in agglomeration phenomenon. And it was confirmed that the morphology of the formed nanodots depends on the material used in the seed layer. When titanium was deposited as a seed layer, the formed nanodots were mainly agglomerated in a rectangular form. And in the case of chrome, nanodots were formed in various shapes. However, in the case of cobalt, nanodots were not formed. These results indicate that materials used as seed layer are considered important factor in the shape of the nanodots. AFM data confirmed that depositing the seed layer above the critical point of thickness interfered with the agglomeration phenomenon, and we revealed thickness of the upper layer affects the density of nanodots in previous study. In summary, the thickness thin film can be a main factor to form the nanodots. This is a reference. Thank you for listening.